In continuation with the topic that we were discussing, that is pupil control system, today we are going to discuss dynamic and steady state response characteristics of pupil control system. In earlier lecture, we have learned about finding of information flow diagram and block diagrams for pupil control system. But for any system, after obtaining information flow diagram and block diagram, we can do any mathematical manipulations and computer simulations. And these two things, that is mathematical formulation and computer simulations, are needed to obtain useful information about systems' dynamic response characteristics. Dynamic characteristics are very important because control systems are not at rest. So steady state conditions usually do not exist. That is very much exemplified in our current topic, that is pupil control system, because we can see that in pupil control system, pupil area, it keeps on fluctuating randomly and continuously over small ranges, even if we do not have any input of light intensity variations. Output of any system can be obtained using input and system characteristics. So the study becomes easier if we ourselves manipulate the input as compared to the systems where input is changing naturally. But in both the cases, input and output behavior is very important for knowing the system dynamics. So here we will discuss qualitative nature of both steady state and transient pupil responses. Steady state response. So here are few assumptions about steady state response. First is input and system variables are constant. Second is there are a set of algebraic equations because there are no rate of changes in steady state systems and hence all derivatives are considered as zero. If steady state relationships are non-linear, as in the case of pupil control system, then we can take help of graphical solutions for studying the steady state relationships. As we have seen in the information flow diagram of pupil control system, in retinal block, input is flux and output is pupillary fiber neural frequency. In CNS block, input is pupillary fiber neural frequency and output is neural frequency of sphincter motor neurons. In sphincter muscle, input is neural frequency of sphincter motor neurons and output is area. And at the pupil level, with respect to area, flux is changing. So we can visualize it here in the form of information flow diagram. For example, in retina, we can visualize a characteristic curve between FP and P. In CNS, we can obtain a characteristic curve between FM and FP. In sphincter muscles, we have relationship between A and FM, and at pupil level, we have a relationship between pupil flux and area. This flux, that is the output of the system, is fed back to the system here at the retinal block. So these are the characteristics at sub-block levels. If we combine all these sub-blocks in a single coordinate system, we can visualize that here the output we obtain, the system is characterized by variation of area with respect to flux, that is the pupillary level, at pupil level. And here FP with respect to P, that signifies the retinal block, and here this coordinate, here the relationship is between FP and FM, it signifies the CNS block, and this coordinate, it shows a relationship between FM and A, that signifies the sphincter muscle subblock. So here in the pupillary block, we can see that there is almost a linear relationship between area and flux, and this linear curve is shifting with respect to variation in the light intensity. Here we can see a parabolic type of relationship between Fp and P. Here this is a somewhat linear type of relationship between Fp and Fm, and again a parabolic relationship between Fm and A. But the important thing is that here if we assume the pupil area here at this point, then we can trace it back through all the coordinates here, here and here, and finally we'll achieve an area this. It will again move here in a cyclic manner, and this iteration keeps on changing, keeps on moving in the cyclic manner until and unless we will reach the value of area that we took at the initial point. So these are through these iterations the system maintains or controls the pupil area. So here what is the assumption is that retinal adaptation and other component dynamics are ignored, because otherwise we cannot calculate steady state, we cannot obtain steady state response. Now, this dynamic response characteristics of the pupil system. It is characterized, dynamic systems are characterized by its response to some stylized inputs, some specific type of inputs such as the transient inputs of impulse and step type, sinusoidal type inputs and some random inputs. Here in this pupil control system we will consider only the step and impulse inputs. We will obtain 4 different pupil responses with respect to the pulse and step inputs for both light and dark conditions. Impulse is considered as infinitely short function and therefore it is a mathematical ideal. So here in this case we will consider input pulse as compared to, in spite of impulse, we will consider input pulse that can be made sufficiently short for the analysis point of view. So we will take help of an instrument, that is pupilometer. Pupilometer we will use to monitor the pupil diameter or area. So this pupilometer, it irradiates the eye with infrared light, considering that the pupil and iris reflectances are different. It causes electrical voltage change corresponding to the pupil size. So we can find out the change in pupil size by calculating the change in electrical voltage. Here approximately 250 millisecond of time delay is observed due to neural transmission delays that are